are connected diverse lack of signature. Cannot things, I mean, globally, it's according to their own area, east of the first. Cases without transition, healthcare policy, HP, cannot favor other pieces. Thanks to can still have the common product that can be benefited by the and how they can be. Then particular can be solved efficiently some minutes, yeah.
Hello, my name is Valeris. I'm a PhD student from University of Latvia. I will show how fuzzy equivalence relation can be used in a clustering process as a similarity measurement. So firstly, briefly introduction. So the standard measure that is used in clustering is distance. And if we have some observations, so the usual approach can be following. You introduce some centroids, and then what you do, you are assigning observation to clusters. Those centroids are closer. Or another way could be you are measuring distance between observations, and if the measure is small enough, you are appending these two observations in the same cluster. So methods is you can choose another method. And here is provided some commonly used distance measures for clustering. The most popular is Euclidean distance. It's often used in various applications. The city block distance, also known as Manhattan distance. Interpretation of this distance is very simple. It shows the horizontal and vertical moves required to reach one point from another. And here is Hamming distance defined for binary vectors. The Hamming distance of the vectors shows the number of different components. So usually these distances are chosen based on the nature of the data and requirement of clustering task. So we will consider the measure which is inverse of distance. It is similarity measure. So if the distance between observations is large, then similarity will be low. This approach has benefits when we are dealing with data sets with outliers or some variations in data, because similarity is less affected by extreme values, so it can lead to more stable clustering results. So for similarity measure construction, we will use a tool called an additive generator. So it is one variable function which is continuous and strictly decreasing. And here is provided some examples of additive generators. For product t-norm, additive generator is logarithmic function. For Lukasiewicz t-norm, additive generator is following. And for Hammacher t-norm, looks like that. Here in special cases, when parameter r is equal to 1, we get just a product t-norm. And now how exactly we will construct the similarity measure? So to construct the similarity measure, we will use following theorem for any pseudometric. This mapping is T-equivalence. Theorem can be proven using the definition of T-equivalence. We are checking this mapping for reflexivity, symmetry, and transitivity. And here is provided example how to construct similarity measure for product t-norm. So first we find a pseudo-inverse function of additive generator, and then using this theorem we are constructing the similarity measure. So the similarity measure what we got is strictly decreasing fuzzy equivalence relations. The same process can be applied for different t-norms, and in next slides we will show how we will see how it looks. And now starts the main part of my proposition. So we will considering two types of similarities: internal similarities and external similarities. By internal similarities, I mean similarities which is calculated for observation from the same clusters. Oops, it is denoted here. And by external similarities, is calculated for observation from different clusters. And also here is a similarity which represents how similar is not observations but clusters. So in general, the clustering problem becomes we are maximizing the cluster's internal similarities for each cluster, and at the same time we are minimizing the clusters similarity. So here is provided some similarity measure for different t-norms. In previous slides, it was shown how to construct similarity measure for product t-norm. And here also you can see how similarity measure looks for Lukasiewicz and for Hammacher t-norms. And now and now let's take a look how to evaluate how similar is to different clusters. So if we have two clusters which may have more than just one external similarity, then what we are doing, we using aggregation operator, we are aggregating all these external similarities into one similarity, and this similarity will represent how similar is these two clusters. And here important thing that we are aggregating only external similarities. Internal similarities are not aggregated here. From aggregation operator, we are asking two things. It must be monotonical and with boundary conditions. And this aggregation operator also is based on an additive generator. So here is provided cluster similarities for different t-norms. Here is for Lukasiewicz t-norms, for product t-norm, and for Hammacher t-norm. And in every cluster similarity, we are here aggregating only external similarities. And when we already have some clustering system, it's time to evaluate how the quality of clustering system. And to evaluate quality of clustering system, we will use an indicator which is based on two components. The first component calculates clusters internal similarities, which we are trying to maximize. And the second component calculates clusters external similarities, which we are trying to minimize. So in the end, we get the following quality index. The closer this index is to value 1, the better clusters are separated. And this index may have also negative values. It indicates that clustering system is very poor. And now about clustering algorithm. So we will use an agglomerative clustering algorithm. It is one type of hierarchical clusterings. So in the beginning, each observation we are considering as isolated cluster. And in each iteration, we are calculating all combinations of cluster similarities. And two clusters which has maximal similarity, these two clusters are merged into one cluster. And also here is the fixed parameter, the similarity threshold. In each iteration, we check if the maximal similarity of two clusters is lower than this similarity threshold, then we stop our algorithm. If not, when we are merging these clusters into one cluster and iterating this algorithm from step 1. And now let's take a look how this algorithm works on data. So for clustering was performed on 3 datasets. Here is provided some information about datasets, its observation count, dataset features, and the real number of clusters in each dataset. For illustration we will use only mall customers dataset because it has only 2 variables, so it will be easier to illustrate clusters in 2 dimensions. And now about process. So here you can see the dendrogram of agglomerative clustering. So here clustering was performed using fuzzy equivalent relations with Lukasevich t-norm. And here on the top, our algorithm starts. So from beginning, each observation is an isolated cluster. And this dendrogram shows how clusters iterative merging process. So how clusters are merged into how clusters are merging. So and if we are not fixing the similarity threshold, then in the end we will get only one cluster which contains all observations. And now if we are fixing the similarity threshold, it means if at any iteration the maximal similarity of cluster is less than fixed threshold, then we stop process. So with threshold 0.52, as we can see, the threshold line crossed dendrogram in 5 points. It means that we got 5 different clusters. And this similarity threshold can be changed. We can increase this threshold or decrease. And here is examples how cluster looks if we are changing the similarity measure. So here is we decreasing this value. So as we can see, these 2 clusters was merged into one cluster. It's also seen here in the dendrogram. Here is example when we are increasing this similarity threshold. So as we can see, this cluster was split into 2 clusters, and also this one cluster was split into 2 clusters. So we got 7 different clusters. And here is providing results of here is provided the results of clustering system quality for each dataset, and we used different clustering methods. We used k-means, fuzzy c-means, and the last three ones is clustering with fuzzy equivalence relations with Lukasiewicz product and Hamacher norms. And these numbers, clustering system was quality. Clustering system quality was evaluated using 4 different indexes. The last one, index IP, it is the potential function, which was introduced some slides before. So this index is based on fuzzy similarities. And the closer the numbers are to 1, the better clustering system, the better clusters are separated, and the clustering system is good. So as we can see, for mall customers dataset, which has only 2 features and clusters are easy separatable, the standard method k-means and fuzzy c-means works better than proposed method. But if we are considering some complex datasets and with large number of features, as we can see that k-means and fuzzy c-means works still good, but as we can see, clustering using fuzzy equivalence relations led us to a little bit better results. So it it means that clustering with usage of equivalence relations can recognize some complex patterns in data sets. So in general, it is all what I wanted to present you in this presentation. So here is some points, the main points of which was talking about. So how fuzzy equivalence relations could be used as similarity measures. So so here we we showed in previous slides it was shown how fuzzy equivalence relations can recognize some complex patterns in data sets, and for this presentation was shown only how fuzzy equivalence relations can be used in hierarchical algorithm, but in general, in each clustering algorithm there is used a distance measure. Distance measure could be replaced with a similarity measure, and so these fuzzy equivalence relations can be implemented in each algorithm. So from my side, it's all. Yeah.
Yes. Okay, so actually, yeah, so I actually have, the FOIA. So, look, you just what you made actually, yeah, you made some comparative analysis, yeah, of various say similarities, yeah, with respect to clustering, right? Yeah.
Yeah.
But actually, so this is a big pile, yeah, of methods, and also we saw that for some data sets, yeah, so this say equivalence works better, yeah, for some, for another one, another works better. Can you tell us from the point of view of data, yeah, actually, not from the point of view of the theory, yeah, from the point of view of data, yeah, we have some data, yeah, so can we make an analysis of data and propose a certain class of similarities that can be good with respect to this data? Or we just, so yeah, because the approach is quite, say, normal, yeah. So we just look how variety of methods works, yeah, on this data, and then we pick up the best one, yeah. But this means that when we change data, we shall repeat, yeah, and this is, so complexity is going up, yeah. So vice versa, yeah. Can we make first analysis of data, yeah, and propose something, at least some class of similarities, yeah, that is reasonable to apply, and just to get rid of another class which is not reasonable to apply.
No, sure, we can do some analysis, but to conclude, if this method will work better or not, for now, I can't answer this question.
Okay, so we can put it for the further research, right?
No, I guess yes.
Okay, so yeah, just take it as a challenge, yeah, for the next conference. Okay,
Yeah.
so thank you. Okay, so this is talk, yeah, actually I'm about the second talk, but the presentation will give my colleague and co-author, Olga Grigorin, I think. And the title is Fuzzy Distance-Based Inequality Relations and Equivalencies in Clustering Problems. So again, we are in the same topic, yeah, and so see the progress.
Wait 1 second.
So yes, thank you for introduction. It's a joint work with Valery and me, and as Irina said already, and Irina from the Institute of Research and Application of Fuzzy Modeling from Ostrava. And yes, I will talk about the generalized distance-like functions. And so they are going to introduced by distance-like functions, the similarity relations and the dissimilarity relations. So we are going to have two dual problems, and then we are going to apply them for the clustering. But just to follow the previous talk, the Valery talked about hierarchical clustering. I'm going to talk about the flat clustering. So all the clustering we could divide on the hierarchical clustering, flat clustering, or optimizational based clustering, and graph clustering. So we will focus on the optimization based clustering. It's a huge class of clustering. When separating the objects, we're thinking about the optimizational problem. And but let me first speak about the definition of clustering. So maybe something which should be before the previous talk, but let it be as it is. So I think that first of all, we should agree what does it mean clustering. I really like the first definition because everyone agreed that the clustering is grouping of data into the clusters. And the grouping is under the precise several conditions. So for every author, the conditions is several. And and also we should precise our condition for clustering, how we group this data. And to be honest, the authors usually speak about similarity at the previous talk. And usually the similarity is given by the distance-like function. Actually, we should not speak only about similarity, but we should also speak about, we would like to speak also about density. And it's not the same, the similarity and density. So density is not produced by the similarity. So the different situation just to play with similarities and density, but we would like to announce that we are we want to work with both, with the similarity produced by the distance-like functions, or in some case by the matrix, and also with the density. So here you just see that example where, which prove the density is also important. So if we take on only the similarity on the or distance-like function, so we separate like this. If we take into account also the density, so it's vice versa. Here, if we take only the distance into account, so we separate into clusters like this. If we use also the density, so we separate with the high density the elements together, then we have these clusters. And yes, the cluster analysis is very useful for the application in different theories. But let me fix also the main problem. So we are going to have the data set D only with numerical data in this case. So all our objects are from the space Rn and dimensional, and you can see that each element has n features. And so we are going to put this object into the car clusters. And actually, if we have or we do not have the number of clusters, it's at that moment an open question. So when this question arises, I will figure this question. So the distance-like function, actually almost all the optimizational based and not only optimizational based algorithms based on the distance-like function. So as Irina already said, that we do not care about the transitivity of the metric. So we use these two conditions from the metric, the symmetry and the first one, and we do not use the transitivity. We use this third condition. It's taken from all the books where the distance-like function are described. So we would like to take the function d, which turns to the infinity when the one argument y in this case is fixed, and the Euclidean norm of the another argument tends to infinity. But to our mind, it seems that first of all, if we normalize the data, we do not need this condition which tends to the infinity, and the other, I would replace this condition with some kind of monotonicity, because if we just in the set R, not many dimensional, then we would like for the distance here we have 0, and for example this is y, which is fixed, and here we would like to have like monotonicity and here monotonicity. So for sure that what the author is doing is that they take every distance-like function and prove the convergence of the clustering algorithm, but maybe just take somehow the monotonicity and prove for the overall. So intuitively, it seems that that one should be replaced by the monotonicity in space Rn. So we should speak about what do we mean by the monotonicity, but we should just deal with also with the Euclidean metric, not in the case of the D, but somehow to relate it with the monotonicity. Okay. And so as I've already said, we are dealing with optimizational problem. So if we have the distance-like function to measure the similarity of the object, then we can go to the general optimizational problem, that one. And what we are doing, so we have the D, our D set of elements. So we make different partitions with the so for the car groups. So we just divide all the elements in car groups, and I call this partitions. So we make all the different partitions, and then we calculate this value. So we calculate the center of of the group of the cluster. And then to each other element in the group, we calculate the distance, the sum in one cluster, and then sum in all the clusters. And then we, solving this general optimizational problem, want to find the optimal partitions of the elements. And what is good, what is bad? That almost all known this flat optimizational algorithms optimize this problem. This means that during the iteration, this objective function, which is without which we are minimizing, is decreasing. But there is a bad thing that it's impossible analytically to solve this optimizational problem because the argument is the partition. And but it's possible to rewrite this problem using the utility function. Is actually the same problem, just rewritten. So we use utility function, which is 1 when the element is in the cluster and 0 if it's not. And we can solve this optimizational problem with the same problems as before for the general optimizational problems. Then I would like to mention also the problem, the optimizational problem, which is solved for the fuzzy clustering. So here the utility function are not only 1 or 0, they are numbers from the interval 0, 1. And so it's indicate the belongingness degree to each cluster. So if here it's not 1, it belongs, then in this case it would be the number from the interval 0, 1. If it's closer to 1, then it's closer. It's the belongingness degree is greater. And so we saw also today in the plenary talk the same. Almost the same. We have another part with non-numerical data, but and we saw here when the do not fall into details, we saw the quantifier too, as I remember. And let us now focus on this expression. So we understand the utility function is greater than 0, less than 1, so it's between 0 and 1. And when we use, for example, 2, it's even less, become less. So by this utility function, we just the lower the value of dn. And what is the advantages of the fuzzy clustering? So by this, really by the lowering this distance d, fuzzy clustering, fuzzy algorithm is better. Fuzzy Kamin, I mean, it's better working with the outliers, and also if the data set, if we could not visually separate the groups, so the like in normal life they're quite mixed altogether, then the fuzzy clustering algorithm works faster. So we use like this idea when we want to lower this distance to propose the algorithm, which is also working not so sensitive for outliers, first of all, and but the algorithm will be some other problems. So we would like first to propose, instead of the distance-like function, generalized metric. In this case, yes, we take like I would say the common definition. So here you see like some generalization of transitivity. Yes, it's this generalization for the conorm T conorm S. Yes, conorm S, and we use the construction of the generalized metric by using the decreasing function, or actually to go deeply into details and into theory, it's additive generator. But to be honest, we just use the millions of different additive generators to generate the different cases. But what we would like to take into account, so you can see here, First of all, yes, it's like a normal distance, like a distance-like function. In this case, it's just a distance. And here you can see it goes to the infinity if we do not normalize the data. We would like to be in the interval 0, 1 still, and this gives us the opportunity to be not sensitive for the outliers. So here you can see the different additive generators of function which we use to generate the generalized matrix of fuzzy dissimilarity relations. And we are going also to involve the parameter t to explain the density or dispersion. So first of all, we have the shape of this function, and by the shape of this function, we should like denote if we want to take into account more the data which are closer. So in some sense, it's also the density. But for the density, we also have the parameter t, which show how far this two is one from another. So we would like to involve the dispersion for our data. And thus, the algorithm is going to be like this. So we use dissimilarity function as we know before, but here we involve also the parameter t. And I will show later on how our objective function, which is here, is sensitive on these parameters t. So its parameter is really very important, and it's important to find this parameter. Is also, if we know this parameter and use a numerical algorithm, it's possible not to denote before the number of cluster. We will see the number of cluster later on. Yes, and so we use this dissimilarity function, and then our algorithm based on the optimizational problem which you see here. And we could find actually we could construct the dual algorithm with a fuzzy equivalence relation. It's completely dual and do not fall into details. And you can see that if in that case, if we are closer, we have 0, then we have 1. It's completely dual, even mathematically, even intuitively. And so in the dual case, we have like this optimizational problem. And I will explain why it's important to start with this problem. And let me show how the objective function looks like in this case, and how the parameter t influence the resulting objective function. So we are going to have the graphs for this function and for these data, and we expect that we have like 5 clusters. And what we are really we expect that this objective function has like 5 extreme points, and for the cluster centers, it has extreme values. And so, first of all, our data are normalized to understand the situation and to value t. If t is 0.5, all the data is like stick together. So we have only one extreme points, and it's here. So it's like a center of all the data. And then just to separate them, we need to lower our parameter t, and we just start to lower that. It's the data became to go to this direction, and you already see here, but maybe it's difficult to see, but they've started to separate from the center. And we just lower much more the parameter t, and here we already see that we have 1, 2, 3, and 5 also, but it's not so clear, 5 extreme points. In that case, it's not important that the one extreme point is like much higher than other. We just are looking for the for these extreme points, and in this case, if we took these 5 extreme points, we could took them at the cluster centers and just after that to make grouping. But we should not go further. So at one point we should stop, because if the T is too small, we have really many cluster centers, and we are not. So at the end, like in hierarchical clusters, we are going like each point as the cluster and the clusters. We are not. It's not our case when we want to have like this. So it's finished. Yes. So just a good news that this problem could be could have a solution using the kernel algorithm, but yes, it's like another lecture to fall into detail how to do that. But really, with the fuzzy equivalence relation, we could use the kernel algorithm when we go to another Hilbert space and use the usual Cummins algorithm there. And at that point, we have to open problems, but the most important is how to choose the parameter T to make this clustering. Thank you for attention, and sorry for.
Well, thank you very much. Can you go back to the side where you make transformation from distance to fuzzy equivalence? Do you have a transitivity? Yeah, you have T transitivity, right?
Yes.
Is it necessary? Because Irina told that we drop the transitivity condition, and transitivity is necessary to make a transition from distances to fuzzy equivalences. Is it possible to observe some kind of weak form of transitivity?
Yes, thank you. I expected really this question for sure, and we use this construction which is fulfilled for the matrix, and we actually in the algorithm we do not use and even for the convergence of the algorithm, but maybe for the convergence it's useful. We do not use the transitivity. We just use this construction. But what is good in this construction? So we do not care about transitivity. We just use all this well-known additive generator and generate this millions of different equivalence relation. But there is one but. I didn't have the time to speak about that. The question is, we just go further like this, or we involve the equivalence relation for each feature and then combine this together. If we would like to do like this, we need to follow some rules. And for example, for each feature, it could be just a simple metric, and then we are combining. We are like if we do not think about the transitivity, it's difficult to understand how to combine that. But if we understand that we go this direction using the real transitivity, we could have the fuzzy equivalence relation, which we aggregate after with a special aggregation function, which preserves the transitivity, and then we should go back to the metric. And that one is good in our case. So generally, we do not care. We could do it for distance-like function. But there are some good points when we could use this T-transitivity. And for sure, for convergence, we should use something like maybe not transitivity, but monotonicity.
Look, so if I take a privilege, the co-author, yeah, look, what is the main idea? Yeah, so here, yeah, what is the difference? Yeah? Here, this similarity acts, yeah, on the vector, yeah. X here is a vector, means high dimensional object, right? And this means that this similarity is somehow unified, yeah, for each, say, component of this vector, it acts in a similar way, in the same ways. Different from this, yeah. So look, so here we have for every feature, component, whatever vector. So we apply different similarity, yeah, so, and therefore there is no here. So here we expect this intransitivity and here not, yeah, because we have this one weak transitivity, another weak transitivity, and so on and so forth, yeah. And when we aggregate, we totally lost, yeah. So, and this is the main idea, yeah? Just to look, I mean, locally, yeah, when I started, yeah, from my introduction, yeah. Okay, so I will stop here just to point out, yeah, what is the difficulty and beauty of this approach. Okay, so thank you.
Thank you.
Yeah. In the group, yeah, of Latvian people, will be given by Martin Zemlitis, and this is joint work with Olga. The title is Fuzzy Equivalence-Based Numerical Algorithm for Solving Multi-Objective Linear Programming Problem.
What do I do laser? This was laser, right?
Yeah.
Hello, I'm Martin, and I will be presenting my and Olga's combined work. And there will be no clusterization here, but we will have problem. Oh, we'll have multi-objective linear programming. Multi-objective linear programming, or MOLP for shorter, is just a maximization problem where we have some arbitrary number of linear objective functions that we want to maximize all of them at the same time, such that some constraints are satisfied. As an example, we have Zimmerman's example where we have two objective functions and some constraints. Here we have one function reaching its maximum, and here we have other function reaching its maximum. Well, they both reach their maximums at different points. The problem is, how can we find the maximum? Well, actually, we have multi-objective optimization. We can't really speak of like the optimum, maximum. We have this Pareto, then we have to speak of this Pareto optimality, which basically says that some point is Pareto optimal if there does not exist another point such that one criteria would have a higher value without others decreasing their value. And for simplicity, I will be denoting objective function as Z. Okay, I will need a pseudo metric, which is extension to basic metric, except we have that if the distance is 0, this does not mean that the x and some other point y, let's say, are equal. And as an example, we have a distance between two functions. Distance between the same function and two different points, and the distance is normed, so it should be between 0 and 1. And this combined with the definition you already saw previously as the equivalence. Well, the example where I have already inserted the distance, if in Luksevich phenom case we have just 1 minus the distance and the exponent. We can combine this to have fuzzy orders, where we get this other case 1 if y is greater, or here we actually have fuzzy equivalence as it was in the previous slide. Okay, now we have everything, and we get to an algorithm for solving the MOLP problems, which is that as a result, it says that the solution to this maximum problem will be Pareto optimal solution of our original problem, where this big P is just aggregation of individual orders, where for each objective function we have an order, and we aggregate them using arithmetic mean. Okay, now the first result I will have to explain because someone will ask me. So what we want for this function P to be fuzzy order, because we want to show that solution to this is actually Pareto optimal to our original multi problem. But for it to be fuzzy order, we need, the problem is state transitivity. We want to preserve it. So whenever we construct this whole thing based on some T norm, we need to choose a specific aggregation function. We can't just freely choose it. In Lukasevich T norm case, we have arithmetic mean. So when we combine all of these building blocks, we get that it doesn't really matter which T norm we choose to build this function, because at the end of the day, the solution Y will still be the same. Okay, now I can go forward. The other simplification is that, oh, I forgot to mention, we are using choosing Lukasevich T norm because it will be just simpler. And as the other proposition is that instead of looking all the x's in the whole search space, we can just look at the vertices of our search space, because in programming, there will be finite number of them, so there won't be any problems. And as another thing, we want to rewrite the function as minimum of different pi, where we choose a specific, we sort of just add index to each of the vertices. And I will be referring to these as a levels, and the minimum of these will be the active level if I mention it. Okay, the function looks like this. The problem is, how can we solve it? Our solution in this problem is this blue dot. Here we actually have like three different regions. The function there is linear, and between them, where the levels intersect, the function is not smooth. Okay, so we tried some derivative-free methods numerically, but it failed because once we added more than two objective functions, this function became almost flat, so it had a problem with the end condition, and so we moved back to something derivative based. So the idea was to maybe we could use subgradient. Now this is the definition, but the interpretation of it is if we look at the function absolute value of x, then the subderivative is just a derivative or gradient if the function is differentiable at the point, but at point 0 of this function, we get that subderivative is just every convex combination of these two. So basically at point 0, we say that subderivative is everything between -1 and 1. This sort of gave us only a theoretical solution, because practically it means that this is the gradient, like the arrows that depict the gradient at each point of a function. This is the solution. So at each point we still choose gradient, except when the levels intersect. But the problem was that if you numerically try to solve it, then, well, we almost never reach the point where they actually intersect. So we were still using the same gradient descent. So the other idea was, okay, maybe we could, instead of to calculate subgradient not only on the intersection, but in some small neighborhood, that's actually called epsilon subgradient method. Well, it sort of worked, but it wasn't satisfactory enough, because so it's like if we for now ignore this area and look at only these two, it would be like we're going in this direction. Then once we reach this, we have like a sharp turn. So it would kind of make sense if we from here would know that we would have to change our direction, so we could like make it something like smooth and sort of smoothen it out, and so that we wouldn't have these like this, but we could go forget the word in English. Okay, so that's why. So the idea is that if we are far from the intersection, we would be choosing only this gradient, but if we are going closer, we will be adding more and more of this, and this gave this sort of gave the idea that, okay, maybe we should just add fuzzy equivalence in some interesting way. Okay, so at some iteration n, we are, let's say at some point y of n. So we can calculate for all of the vertices the value of pi of yn, and we can simply just order them from the smallest to the biggest. Then we say that our weight v1 is just 1, and v2 is exponent of minus beta times the distance. So the idea of the constant beta is because we want that if the distance is small, then we want the weights to be equal. But if the distance is big, we want to have that v2 is a lot smaller. But because between different examples, we might get that the idea of what is big and what is small might change. So we wanted to somehow norm it. So this is where we are at now. Okay, and then we just add them up to give ourselves the direction of our search. And then we need to find a step size using the adaptive line search method. Basically, if given a direction and point, we start at alpha equals 1, and then we just come back slowly until we have the point where, in our case, the function would have a value that is bigger than we are at now. And if there isn't such alpha where we would take a step and have a bigger value, then it would mean that we should be some at the optimal solution. Well, and then we just find the next point and repeat. Okay, I quickly wanted to show what I mean by subgradient and epsilon subgradient method. So as I showed previously, subgradient method is basically gradient method if the function is differentiable at some point, but if at some point where in our example the two levels intersected, we just took the average of how many levels they're intersected. And in epsilon gradient method, we did the same as here, except that instead of at the point where they intersected, we did the same at some small neighborhood. Okay, this is how it looks like. So in the beginning, the example I showed at the beginning, the Zimmer ones, this is how it went. This is equivalent. This is our approach, the algorithm we proposed. The red one is the epsilon subgradient method, and the V one is the subgradient method, and I combined them in the same plot. Okay, in an example where we have three functions. So this is the same as Zimmerman example, except we added the third function. V3 is just minus x1 minus x2. Here we can see that the subgradient method failed to converge. And in final example, when we added fourth function, just x1, actually both of them failed to converge. Well, this might seem that our method is this really good, but actually the biggest issue is that subgradient method isn't descent method, so we can't actually really choose the outline search to find its direction. We would have to choose like a constant size or constant step size or constant length step size for it to work, because in subgradient method we might have an iteration where we actually choose a direction in which our function would be decreasing. So that's why it failed to converge, because it took a direction where the function just did decrease, which actually sort of is a good advantage for our method, because we can be for sure that we can use adaptive, like the line search method for finding step size. And except that we know, yes, the other issue is still constraints, because I chose the same Zimmerman's example, except I started at a different point. So the issue was that the method tried to went outside, but because of projection, it was pushed back. So it like sort of jumped around the final stretch of the problem optimization, which is still an open problem. Because we can't really guarantee that there would be a case where, because of this, the algorithm will just fail to find the optimal solution. Also, the problem isn't the problem isn't if our optimal solution is somewhere in the middle of our set. So that leads to what to do next. Okay, so I showed that in our algorithm, which we made a combination of just two gradients, but maybe it would make more sense in some examples to combine even more of the gradients for different levels. So we still need to find a good way to do this because it isn't as simple as it was in the case when we just have two of them gradients. And we want to generalize this in a way that we would separate the algorithm from linear programming to like more global case where we just have a maximum problem. And yes, the third one, as I already mentioned, is the Williams constraints. Thank you.
Because I just struggled, when I was listening to your presentation, with particular problem, which you showed at the beginning. This is the Zimmerman problem and the general approach. Actually, the question is, so your approach, so this Zimmerman problem, is some isolated example, or this is a representation of class of other examples. So tell us something, because
So the question is why it's called Zimmerman's example.
yeah, so why, and then the question is, how the peculiarity of this example influences results, or all results are about this particular example?
Oh, we're just choosing this example because sort of if we change them functions, then, well, it might change where the solution is, but it wouldn't change because it would, well, it would be still more or less the same. So we're just keeping what we already know and adding more to it. Okay.
It will help me, because you then focused on various spaces, where gradients are important, and then it wasn't clear, so you are speaking only about the properties of this, or so it can be really generalized. This is just recommendation, to
Yes, I understand.
us, so to make our job simple. Okay, so thank you. If there are not other questions, so thank you again. Focus on. And now from 70 we mostly to proximities. And so
Yeah, I'm behind you. I just prepared with the long cable. Okay, thank you for the nice introductions. So as you mentioned earlier, we had articles from Latvia cluster, but now we move to the different, but still is some kind of similarity to the term Ostrava, because you had a common article, so we are moving with light similarity in these directions. But okay, let's continue. So this talk is about proximity relation and conformance measuring evaluation. So it could be, let's say, a lighter version from the mathematical point of view, but see how we can apply it. And my co-authors are Milan from Belgrade and PhD student Nina from Bratislava. Okay, just to, oops. Oh. Yes, okay. Yes, okay. So introduction, just check the time. So for introductions and motivation, then a little bit about our function proximity and conformance. And then how we aggregate by convex combination of possibility and necessity measures, where we apply fuzzy linguistic quantifiers and finally concluding messages. So let's put it into the more introductions. When we should find, let's say, the most the best entities which are as close as possible satisfies our needs. We have a lot of elementary conditions, and then okay, we aggregate them by different aggregation functions. But always the first step is how to calculate elementary condition satisfaction, which should be usually in the unit interval. Okay, but the elementary condition are very simple, relatively simple cases when we have numeric attributes and apply fuzzy sets in the sense, let's say, short distance, 750 meters with intensity 0.7 and so on. But we're working with categorical, either nominal or ordinal attributes or binary attributes. Our situation is a little bit different, so we need impact, proximity, and conformance. But a little bit go to the history. These two functions are initially proposed for fuzzy relational databases. The main goal is to find if, because in traditional database, redundancy is very easy to recognize. But in case of fuzzy database, it is a little bit problematic. So they were applied in order to recognize how our records are similar, or even for clustering relatively similar data. But in our work, we are going a little bit in different way, not to find how they are together, how to find their more, let's say, difference, or how they are close to our condition which should be satisfied. Okay, so let's show you a very, very simple example. Let's say requirements, one atomic requirements for a balcony of a room, and the similarity between yes and no, in the sense that when someone says that hotel room must be presented, then yes and no have nothing in common, so it is clearly a requirement. If for us is absolutely irrelevant, could be say value 1 or excluding from the conditions, but there are several other options, like say just preference, strong preference, or weak preference. Let's say if it is weak preference of balcony, does yes or no could be quite similar. So balcony room without balcony cannot be rejected, but it should be lightly punished. Okay, but when we move to the categorical data, in this case, a situation more categorical, it is a little bit more complicated. In the past, as I mentioned, fuzzy relational database, so go again to this topic, then there was 3 requirements, clearly reflexivity and symmetry, but also min-max transitivity in order to see, let's say, x1 similar to x2, x2 similar to x3, then x1 should be very similar to x3 in order to find, let's say, cluster or remove them. But when you try to explain for the purpose of calculating satisfaction atomic elementary conditions, this is a general rule which consists only of symmetry, and the second one is reflexivity, because when we are working with nominal data, they could be similarity among them very any value, but when you consider ordinal data, in that case, let's say very small, small, medium, high, very high, in that case, we should add more properties. And we see that, let's say, if you look at the first row, it is clearly that when you have this our reflexivity, and then as we're moving further, that the similarity should be less, less, and less. In the case, it is not strict, since it seems simply that 2 linguistic expressions are the same, but between them are difference, and finally, difference could be 0. There could be similar with 0, or maybe lightly above 0. And then directly from this, we could say that we have in our case transitivity. So simple when we have, let's say, very small and very high, then from very small to small and small to very high, on the very small to medium and medium to very high, we always should keep this property in order to keep our, let's say, table of proximity measures consistent. So and then, okay, this was the first part, but generally, when we have numerical proximity, we have infinity options between 0 and 1. But when we apply linguistic proximity values, because this value ABC, it is for people quite hard to assign numerically, we could go to the linguistic terms. But let's, when we look, we need, for instance, when we have 4 categorical data, we need 7 different linguistic terms because on the mind diagonal is only 1, and then to fill half of matrix, the second half is symmetric. Or for 60, n is 6, we have 16 linguistic terms, but golden rule for humans, you know, from the psychological world from the future could be more than 9 is complicated to assign. So in this case, it is easily to present, let's say, similarities by family of linguistic terms, and we have, in our case, exactly 9 of them. In the middle is more or less similar, the same, and fully different. But the question was at the beginning that we should keep the order and the mean transitivity. But when we are working with fuzzy numbers, it could be a little bit complicated. But when we keep this as a Ruspini partition, is relatively easy. We could work only with indexes. So this is also interesting to see that when we had in the morning a nice session about fuzzy rule-based systems, that the set of criteria for the very good linguistic variables is expressed here to have in this work to have a interpretable model. But when you look here, we have several criteria, but for majority of them false Ruspini partitions, like leftmost should be 1, native very distinguishable or not lightly distinguishable, etc., etc. Okay, and this could be our, let's say, table of how someone could assign similarity. We have in this case it is all mind diagonal, and then you could say almost more or less similar, fully different, etc. So anyway, more than 9 pairs is even hard for people to express them. Okay, so in that case, it is not very complicated. We don't need to, let's say, calculate other ways how to measure consistency of proximity values, because we see clearly that L5 is lower than L6. So we don't need to calculate this, but what is it is relevant? Okay, theoretically we could say that this is enough, because we could say very low and medium in our case is more or less similar. So this atomic condition is expressed by triangular fuzzy number more or less similar, and then we add more atomic conditions and then apply fuzzy arithmetics to get the final value. But generally, we could have people that could say between very small and small. I'm not quite sure. On the other side, in a data set, you could have numerical data, categorical data, fuzzy data, even for one attribute if you not keep the structure of databases. So when you, let's say, numerical data divide into equivalent or another kind of intervals, borderline cases could be problematic. So in that case, let's say user could say very small, but in value is between, let's say, small and medium. So in that case, we need to calculate, this conformance measure, which was initially also developed for fuzzy relational databases. This half part is just for keeping for similarity. So we see this second calculates how our maximization from as user expectation to 1 and the second one, and for the second attribute, and then by the minimal value. Okay, and there's also when we have, let's say, several atomic or more atomic conditions on proximity with user expectation to the data is between 0 and 1, or when we apply fuzzy data, we, as mentioned, we have triangular fuzzy numbers for each atomic conditions. When we apply triangular fuzzy numbers, it's no problem because we can find which is dominated by another one, so minimum maximum is not problematic to find. Okay, that's just a bit remark about the how we could aggregate them. Then, so my colleague Milan, they worked with some kind of application in radar images, etc., to recognize it. And then the idea was to apply quantifier most of, because when you have numeric similarities, this is very simple. And then quantifier is quite nice because it is neither pessimistic, it means the conjunction with all atomic conditions should be satisfied, neither very optimistic, like the junction we want to be satisfied. So we see if of all atomic conditions are very lightly satisfied, in that case, entity is rejected. When are very strongly satisfied, then will be fully accepted. The question is whether we could have flat area or not. It depends whether we could find a subset of entities very close to our requirements, or if you keep the, let's say, strict one, in that case, a nice ordering for all atomic conditions. Yes, but also, as I mentioned, we have expressed by triangular fuzzy numbers and aggregation by the quantifier. So when we see we have, let's say, when we have all atomic conditions expressed by triangular fuzzy numbers, it is clear that by sum of triangular numbers is triangular, and then arithmetic mean of them is also triangular because with multiplication by parameter, which is 1 divided by number of atomic conditions, we still have triangular fuzzy numbers, and here could be the solution. So the question is, which is where is the final value? So when we apply the falsifications at the before, then we very clearly have a one numerical value. But when we keep uncertainty even to the end of our work, in that case, we are finished here. And then the question is how to calculate. We have possibility and necessity measures. Possibility is optimistic, necessity is pessimistic, and these cover, let's say, two borderline cases of, let's say, users, which can be optimistic or pessimistic. And also the next option is to apply a combination of possibility and necessity measures in order to, let's say, keep balance between these two extreme cases. The only problem could be in this case when you have strict under necessity, because in this case, necessity means that force should be met. In that case, will be greater than 0. And in our case, core is met only when you have very, very strict case that similarity is equal to 1. So in this case, when you have it is maybe a better option to keep most of as one kind of flat area. And also if you could, it is interesting when we could try to apply the opposite case, quantifier view, it is quite problematic for both the borderline case of quantifier view. But anyway, in this case, they are interesting. Most of them are satisfied, so we could apply this. Whether it is linear or non-linear is also a matter of problem we apply. So I think I am more or less on the time, just to look some kind of main observation of proximity and conformance are suitable for evaluating entities. They were used in the past for fuzzy relational database, especially measure which was called similarity. But as I mentioned earlier, due to the problem, the max-mean transitivity was excluded, and then the measure got named proximity. But for the proximity, we add the additional property, which is, let's say, the keep monotonicity between linguistic terms, and also we combination of possibility necessity measures and also at fuzzy triangular numbers to keep the user's expression like more or less similar or something like that, when it is not easy to express by numbers, because you see that when you apply between numbers 0.75 or 0.76 for the people is almost the same. So, and also future work, some formalization and also application in data mining also could be applied fuzzy functional dependencies, because proximity and conformance are basis for fuzzy functional dependencies, which are covering different data types, even mixed data. It could be very nice, let's say, to explain whether correlation exists between two attributes, but also the direction of correlation. But anyway, it is a topic for the future work. And this is the end of this talk with our very recent activity. And finally, thank you for your attention.
Objection towards the term linguistic term. You are dealing with fuzzy partition, with categories, and to be better oriented among them for application, you name them by some expressions, but these are not linguistic expressions. These are only names of these categories, nothing else. There is no linguistic behind that.
Behind. It is still, it is when you have look of the main definition of a linguistic variable, then we have also the domain, the name, the terms, and this that each term is expressed by function.
Simply categories.
Simply
categories, nothing else.
Nothing.
And my question is, what is for you quantifier?
Well, the quantifier, it depends on the quantifier. It is, let's say, most of it is increasing functions, but when we apply quantifier of u, it is problematic. It should be decreasing functions, but the problem is that not a single attribute meet the problem that could be problematic case for this case.
The domain.
The domain is between 0 and 1 because or proportion not a single attribute meet or all of them meet the conditions. So it is always increasing function. If we discuss most of or let's say about half, it could be more or less triangular functions. When we have domain about the proportions. So in our case, the proportion of satisfied atomic conditions. Because when you have quantifier for linguistic summarization, this proportion of entities meet the condition, but in our case, it's proportion of atomic conditions meet by the entity, and then we see whether it meets few about half of most of them, most of atomic conditions.
He measures power, relative power, yeah, and then he applies quantifier, yeah, just to understand how this power, yeah, can be characterized, yeah, with the help of 0-1 measurement, yeah. For example, yeah, if you have yeah, all elements from the big sets also means most, yeah, you know, first power and then quantifier. So that's the point. Okay, this is just yeah, because we had this.
Okay.
Yeah, also such.
If you return to slide 6. Slide 6.
No, your problem. It's working. Okay. Yes.
Okay, so.
Yes, I have two related questions here. Why do you ask that all the inequalities are strict?
Strict equal.
Some can be less or equal, and I'm interested in minimal.
So okay, when you look, sorry, the slide.
No.
Okay, when you look at the previous slides, this means that this is categorical values. Let's say very small, small, medium, high, etc. So in this case, between similarity between very small and very small is 1, but between let's say very small and small should be lower than between very small. Between the same value, let's say very small. But when you have small and very small, it should be strict. Otherwise, it will be considered as the same linguistic term. Yeah, same linguistic term. So we should keep a strongness. And here and the end is simply mean, let's say illustrative example, very short distance and beyond walking distance. So it could be 0. But it also could be situation where, let's say, very high and very small are more very lightly similar. So in that case, you keep this.
So if you remember, Olga also had something similar, yeah, when she required that the norm, yeah, of how it was x, yeah, similarity xy, yeah, when y, y is fixed and x goes to infinity, yeah, this norm also goes to is larger to 1 or something else. This is the same, yeah. So 1 is fixed, and then when so the power we are, yeah. So the And the more close to zero we are.
Very, but yes, but we only have categories, so we have a discrete, not the continuous, but discrete. Yes. Yes. Yes, yes, yes. And also just remark for the second one, for the second, just we simply means that we have very, let's say, very small and very high, that combination from very small, we could go to the small and then very high, on very small, medium, and then very high. So this, it is the reason why we keep mean transitivity. Mm.
So no numbers, yeah, for example, yeah, in case of Olga, yeah, so we have numbers, real numbers, yeah, just to estimate. Here, we have words, yeah, small, more or less small, blah, 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 yeah, but this again an ordinal scale, yeah, of word, and therefore we just have similar estimation, but using different scale, that's the point. Okay, so in any case, so thank you.
Yeah, thank you. What is for you?
Yeah, yeah. And so we are, I ask you to introduce your colleagues, yeah, and then to tell us about topic and the content, yeah, okay.
And we make it like full size. Good evening to all. My name is Pragya Gupta. I'm a PhD student in Department of Mathematics at Indian Institute of Technology, Kharagpur. So this work is done in the collaboration with my advisors, who are like Professor Dejani Chakraborty and Professor Devashri Guha, and with my seniors. So today I'm going to talk about the retinal vessel segmentation based on fuzzy histogram feature enhancement with the input-bound Peregrine-based pre-aggregation operators. So as the title is related to the eye, like the segmentation related to eye diseases. So this is the outline of my presentation. Yeah. So this digital fundus imaging in ophthalmology plays an important role in the diagnosis of many pathological disorders such as like hypertension, stroke, and cardiovascular diseases. In 2018, the Google Research Group has published his work, and they have identified that these cardiovascular risk factors can be identified through the fundus images. So these computer-aided image analysis of the eye fundus is highly desirable for many diagnosis of many retinal disorders such as glaucoma, age-related macular degeneration, and the diabetic retinopathy, which is the most frequent disorder because as the worldwide, this diabetes cases day by day are increasing. So if any person is having diabetes, so there's a high chances that the person can have diabetic retinopathy, and it affect actually our this vision. So this is an example of this fundus image. This is the posterior part of our eye, and it can be captured through a fundus camera. So there are different kind of features in the fundus images. If any person is having kind of retinal disorder, so the variation starts appearing in this fundus images. So for overall, if I'll say these, if you see these edges, so this is called a blood vessels. So our eye is having two kind of vessels, which is large vessels and small vessels. So then if you see the focus on this are the large vessels, and there are like some small minute vessels are there, which is a small vessel. So this is the optic disc area. So here our main focus is to segment these blood vessels so that we can analyze where the changes are appearing, and any clinician person can use to identify the disorder. So during any progression of retinal disorder, the vasculature features change, and which can be visualized through the fundus images. And for example, like leaky blood vessels, and where new blood vessels start growing. For example, this is the fundus image, and this is the case of a diabetic retinopathy. If we'll focus in the optic disc area, if you see the small vessels start growing. So if we can identify and we can precisely segment this one, So any clinician can directly give the decision whether the person is in which stage of the disorder. So in this direction, like so many attempts have been made, which can be categorized into two parts. One is like traditional based method and one is like deep learning methods. If I talk about the traditional methods, so some are the image processing based method and some are the machine learning based method. So like several attempts have been made on the image processing based method, which are like mathematical morphology, match filtering based, line detection and fuzzy rule based. In machine learning based model, first, we will implement all these image processing technique, and then we use any k-nearest neighbor output detector machine for pixel-wise classification. In the deep learning-based method, we can directly give this fundus image to any model for segment these vessels. But here is a drawback in the traditional-based methods, since like as you can see, this is the color fundus images, so it is having three color channels: red, green, and blue. In the traditional methods, what's happening? They are trying to utilize only green channels because there's a high contrast change between the background pixel and the foreground pixels. So directly neglecting all the color channel information like the red and blue, it can cause it can harm the decision. Plus, in the deep learning method, we can directly give this fundus images to any model. But as we know that in the medical domain, we don't have a huge amount of data. And also, if you are training any supervised model, so we need a manual annotation. But these manual annotations, as you have seen in the first slide, this is the manual annotation. This is a very tedious task for any ophthalmologist to do. So here and also one more point. Here, if you see, this is one vessel, and here's the color difference in between that, which is called a central reflex pixel. So here also in the traditional based method and also in the deep learning based method, what's happening? Yeah, they are not they are not capturing these pixels, because if we are just applying the traditional based method, so this pixels is missing and this vessel will be divided into two parts, which can affect our decision making. So for that, yeah. So for that, we have proposed an unsupervised vessel segmentation method by fusing all the color channel information using an interrelationship handling pre-aggregation operator. And also we have tried to enhance this small vessel information using modified dynamic fuzzy histogram equalization technique. So the work can be categorized into three parts. First, we have constructed the Born-Trigonometric pre-aggregation operator. Then we have proposed the vessel segmentation algorithm by fusing all color channel information. And lastly, we have used the modified dynamic fuzzy histogram equalization technique to enhancing the small vessels. Before going to the methodology part, some basic concepts are required for the construction of the Born-Trigonometric pre-aggregation operator. As previously, like so many presenter has like given the about what is the aggregation function. So this is like a kind of fusion tools. It will take the information from each data sources and it will generate a single element. So if any function g is said to be an aggregation function if it satisfies two properties, boundary condition and monotonicity. The general one form of Born-Trigonometre is existing in the literature. This is the basic form of the Born-Trigonometre operator, which will behave as an aggregation operator. But here we want to use as a pre-aggregation form. This is the generalized form of the Born-Trigonometre operator, which is defined on the three tuple of aggregation operator M1 star, M2 star, and C star. By changing and by choosing these different kind of aggregation operator, we have like different kind of Born-Trigonometre functions. But here we want to make the pre-aggregation operator because, as we can see, and in this first definition in the aggregation function, here we will have a monotonicity increasing in every direction. But if we are, these vessels are kind of H-type features. So if we'll take increasing in every direction, so what will happen? The noisy pixel also can be counted as a vessel. So we want an increasing in a particular direction. So for that, we have constructed the Born-Trigonometre pre-aggregation operator, and this is the general form of the pre-aggregation form. And if we'll impose some properties on C star and M2 star, then this will behave as a pre-aggregation operator. So for that, if this C star is the left conjugative aggregation operator and M2 star is idempotent and it's increasing in array direction, so this form will behave as a pre-aggregation operator. So we have utilized this form in the color channel fusion to segment the vessel. So this is the whole framework of the vessel segmentation algorithm, which can be divided into 4 stages. First is like a background feature elimination. Second is vessel feature extraction. Third is like prominent vessel feature map enhancement. And the lastly is the comparison of the ground truth image with the predicted one. So if you first will see, we are just fragmenting all the color channels in the red, green, blue. And because we are focusing on a particular features like the blood vessels, so we need to suppress all the background features. So here we have used this median filtering technique, and one of the technique is like contrast limited adaptive histogram equalization. And we have calculated a difference between this median filtered image and the Clahe process image. And corresponding, we have generated the feature the response after after calculation of the difference. So these are the responses we have generated for this responses for corresponding red channel. This is the for corresponding green channel, and this is corresponding blue channel. And we can see the some of the vessels are appearing in the response of the green. However, like we are not able to visualize in the red band and in the blue band. After that, we have combined these all three channels using a one parameter pre-aggregation operator. First, we have taken at a pixel location a 3x3 neighborhood, and we have calculated the absolute difference, and then we have combined using this pre-aggregation form. So finally, the feature map will be generated, and for visualization purpose, we have enhanced this one. After that, we can apply the thresholding method and some morphological operation to generate from the binary map. But here, after this step, what happening? The most of the large vessels will appear, but some of the small vessels will miss. So because of that, we have applied one more stage in this process. So what we have used here, we have used the grid level of these feature map to construct a fuzzy histogram, and then we enhance the area where the small vessels are appearing, like such as if you can see here, some vessels are here, but we cannot see properly. So for that, we have enhanced uh, this green channel using a fuzzy histogram equalization technique by using the gray value information or the previously calculated feature map. So finally, we have enhanced this image, and the same technique we have applied for separation of the background features by applying this median filtering and the Clahe. And finally, from here, we have generated a binary map. So using these by stage 2 and by stage 3, we have like two kind of binary map. Then we have combined finally. So finally, final generated map will look like this. So here we can see this is the ground truth which is already there, and that is labeled, and this is our generated segmented image. So we can see like it's almost try to segment all the vessels properly if you'll compare with the ground truth. Next, to see the performance of this model, we have chosen two publicly available data set, which is Strive and STARE, which is a collection of fundus images. To check the performance of qualitative and quantitatively, we have used some evaluation measure, which is accuracy, sensitivity, and specificity. First, we will see the qualitative analysis. So here first we have shown that when we are using only the single channel information and when we are using all information, what variation is coming. So this is the ground truth image and this is the original fundus image. When we have taken only the single channel, this response is coming. And when we are fusing all the color channel information, so this response is coming. If we focus in the near the optic disc area, this area, in the ground truth and all these two responses. So in the green channel, what is happening? Some of the small vessels are not appearing. However, it is in the ground truth and also in the color fusion. So if we are totally neglecting all the information, so it can we can miss some information in the vessels. So for that, in this part, we can see that in the qualitative terms, the model is performing better. And also we have tried to compare it with some pathological images. This is the fundus images, which is having some pathological features. And here we have tried to compare with the manual annotated images. So if we'll focus here, the shape of the vessels and the shape of the vessel in the our generated method, it's almost similar. However, the manual annotation is like little bit difference. This we have verified with some clinician. And also if you see here, here's one vessel that's like little bit visible, which is not manual annotated by in this image. So if we'll directly use these fundus images in the deep learning method to train the model, and we are using this ground truth, so it can affect the result. So because it will generate the similar map in the deep learning methods. But in this our proposed method is try to preserve the geometrical shape also try to predict those vessels which are not properly visible for an ophthalmologist during a manual annotations. Yeah. Then we have done the quantitative analysis in terms of accuracy, sensitivity, and specificity over these two chosen data sets. And we have compared with several state-of-the-art methods. We can see in the derived data set case, the accuracy and sensitivity is higher compared to this traditional based method also and the deep learning based method. However, if we can see the specificity is little bit in between that, because I have mentioned we are calculating the confusion matrix with respect to this ground truth. As this vessel is not here in the ground truth, so it will calculate it as a false positive, which will affect the specificity. So because of that, it is like little bit moderate. The same trend is appearing in the straight data set case also. So here the accuracy is compared to our others model is better, and also the sensitivity rate and same trend is happening in specificity. And also this is unsupervised algorithm, so we can give to any clinician so they can directly implement in just 1 second they can generate a map. So they can use for their purpose if the vessels are not appearing, like in the case of pathological case, they cannot easily see like where the vessels are there, so they cannot give any decision. So in conclusion, yeah. So here we have developed a segmentation algorithm for extracting the blood vessels from fundus images using an interrelationship Handley aggregation operator. And also we have enhanced the small vessels using a modified dynamic fuzzy histogram equalization technique. And we have also we have seen the performance of the model using this drive and stray data set. And it shows that in qualitative and quantitative, the model performance is better compared to the state-of-the-art methods. But in future, we will try to use some more color spaces so that we can enhance the sensitivity rate. And also we are trying to collecting the response of the doctor, how much it is feasible for them, like how much it is like advantage for them, like whether it will be feasible to easily analyze these retinal disorders from these annotations. So these are some of the references which we have used for this work. Thank you for the listening. This is our small member in our family too. So yeah, it's like always naughty.
This small boy also contributed.
Yeah.
Yeah, exactly. Thank you for your talk.
Yeah.
I'm wondering what is improved quaternary aggregation operator does. How do you interpret it? What is your explanation why this improved quaternary? Yeah, and no, what is your interpretation why it works? Why does it work? Why does it work? Do you have an idea how it works and why it works?
So if you see the definition of the bond within a mean, let's go with the definition part. Yeah. So here if you can see, it will try to interacting. If we are suppose we are having n number of elements, so it's try to interacting other than -1 n number of elements. If we are just take any other operator like the maximum and average, so in the average case, what is happening? We are just giving equal weights, and in the maximum case, we are taking this like the it can also happen. The noisy pixel can have the maximum value, and if we are directly implementing this maximum function, so it will choose this noisy pixel, which can be then it is like a false positive. So it can affect our decision making. So here we have try to use this interaction thing, and also I mentioned about the central reflex pixel. Like if we use any other operators, what will happen? some of the vessels, like this one, if you see here, there's a contrast between in the middle.
Mhm.
Okay, so we want to try to interact all the neighborhood information. Otherwise, if we use any kind of operators, just like maximum, so it will just take the edges part, the maximum value. So it will just divide the vessel into two parts, not the whole. So that is the reason we are trying to just taking the interaction between the neighborhood information. That's why we have used this one phenomenon.
Mhm.
I think it's clear.
Yes, but I guess you're looking for some specific information because there's some bright spots also here.
Yeah,
And
actually,
and you don't want to take these into account, I guess.
yeah, we
And
want to,
you want to somehow incorporate the knowledge what the vessel looks like,
yeah,
I guess.
actually here, sir, here our main focus is to extracting the vessels,
Yes.
and we are creating a pipeline so that we can incorporate all these vessel information and we can combine with any algorithm so that we can just divide all the stages of any diseases. So we are trying to creating, this is the first pipeline, and then we are just focusing.
Uh-huh. And how do you take this vessel information into account? Because, vessels have a certain aspects, and so for example, you don't want to have these take these bright spots into account. So
Yeah.
it's and your bond ferry index is even different than you have an improved bond ferry index.
Yeah, actually.
So of course you can always merge different color channels and
Hmm.
information, but what specifically is so good about your improved method? So I don't know exactly.
Yeah.
Yeah.
In terms of improvement, like if we can take, like we have tried, we have also experimented in some other operators also, and but we found because of some other aggregation operator, what's still happening, the sensitivity rate is going down. Means the like it is affecting the classification of vessel. It is not like exactly giving where the vessels are there and where something else. Like if you see this is spots, as you mentioned, these are the spots. These are also some pathological features, which is called microaneurysms, which is the first stage of diabetic retinopathy. But like as I mentioned, this blood vessels also, so there are different kind of features in the fundus images. Like if any person is having like some any retinal disorder, so the changes start appearing in the vessels also and at the background also. This is also a part of vessels, but it is not visible. That is like more background. So there are different imaging modalities. So this is the first modality. This is the fundus, is the basic one, which is non-invasive. Like we can directly capture the image. Otherwise, if you go for this fundus angiography, so this is the kind of invasive techniques. Like so we have to like inject or something like we have to do, then we can generate the image. So if we'll talk about this operator, uh, here in this work, like we have experimented in several aggregation operator, but here I'm not shown. In that terms, this bond pairing, I mean, the performance of bond pairing is better. So that's why we have chosen that one.
Mhm.
Just
I think-
experiment, and then also they show.
And then we have like moved to the
Yes.
theoretical part.
Yes.
Like it's
But of course, sometimes there should be
Yes.
an explanation. Would be nice to have an explanation. Yes.
Okay, so thank you so much.